Hello, students! Today, we are going to start a very interesting topic, something that is happening all around us all the time. We're going to talk about motion. It's a basic but very important idea in physics. And I promise, by the end of our session today, you will understand very clearly how we describe it. So, are you ready? Let's begin. I want you to just take a moment and look around you, right where you are sitting. Is everything completely still? Maybe the blades of the fan are moving, or perhaps you can see vehicles on the road outside your window. You will notice that things are always moving around us. You see, this is a very common observation in our daily life. We see some things that are not moving, which we say are at rest, like your study table. And we see many other things that are moving or in motion, like birds flying in the sky or cars on the road. So, how do we define motion in physics? The definition is actually quite simple. An object is said to be in motion when its position changes with time. Please remember this sentence. It is the key definition. An object's position changing with time. That is motion. But here's an interesting thought. Is it always so easy to say if something is moving? Well, it can be a little tricky. This brings us to a very, very important idea in physics, the concept that motion is relative. Let's try to understand what this means. Now, this is a fascinating idea. It means that the very same object can look like it's moving to one person, but at the exact same time, it can look completely still to another person. How is this even possible? Let's take an example. Imagine you are sitting inside a moving bus. When you look outside, what do you see? You see the trees and the buildings moving backwards, right? But think about a person who is standing on the road. For them, the trees are not moving. For them, it is the bus and you sitting inside it that are moving forward. Now, what about the person sitting next to you on the bus? For you, that person is at rest, not moving at all. You see? Whether something is in motion depends on the observer. So let's think about this question. The walls of your classroom or your room, are they at rest or are they in motion? To you, of course, they look like they are at rest. But what if someone was looking at the Earth from outer space? For them, the whole Earth is spinning and moving, so the walls of your room are also moving very, very fast. So you see, it all depends on your point of view. So to avoid all this confusion, scientists need a common ground, and for that, we use something called a reference point. We can also call it the origin. It is simply a fixed point that we all agree on, which we use to describe the position of an object. For example, if I say my house is 2 kilometers away, it's not very clear. But if I say my house is 2 kilometers north of the main post office, now it is clear, because we have used the post office as our fixed reference point. Okay, so now we know we need a reference point. But how do we describe the actual path that an object takes? To do this, we use two very important quantities, distance and displacement. Now, these two words might sound similar, but in physics, they are very different. Let's understand them very carefully. To make things simple, let's imagine an object moving in a straight line. We will say that its starting point, or reference point, is O. By using this simple straight line motion, we can see the difference between distance and displacement very clearly. First, let's talk about distance. Distance is the total path length that an object has covered. Think of it as every single step you take on a journey. It's the actual path traveled. We only care about how much ground was covered, not in which direction. Let's look at our example. Suppose an object starts at O and travels to point A, which is 60 kilometers away. Then it turns around and comes back towards O and stops at point C, traveling another 35 kilometers. To find the total distance, what do? We simply add the two parts of the journey. So 60 kilometers plus 35 kilometers, that gives us a total distance of 95 kilometers. Simple, right? Now, let's look at displacement. Please pay close attention because this is different. Displacement is the shortest distance between the starting point and the final point. You can think of it as a shortcut, a straight line from where you started to where you ended. Displacement tells us how far out of place an object is. Let's go back to the exact same journey. The object started at O. And where did it end? It ended at point C. So, what is the shortest straight line distance from O to C? It's 25 kilometers. So, look at the difference. The object traveled a distance of 95 kilometers, but its displacement is only 25 kilometers. This table is very, very important for your exams. It helps you remember the differences. Distance is the total path, a scalar quantity, which means it only has a value. Displacement is the shortest path, a vector quantity, which means it has a value and a direction.
But look at the last point. This is very interesting. Distance can never be zero if an object is moving, but displacement can be zero. Let's explore that last point a little more. Let's imagine our object travels from O to A, which is 60 kilometers, and then it travels all the way back to the starting point O. Now, just take a moment and think. In this case, what would be the distance and what would be the displacement?
So let's see. The distance is the total path. So 60 kilometers to go and 60 kilometers to come back. The total distance is 120 kilometers. But what about the displacement? Well, where did the object start? At O. And where did it end? Back at O. Since the initial position and the final position are the same, the shortest distance between them is 0. So the displacement is 0.
All right, now that we have understood the theory, let's see if we can apply it. We're going to solve a numerical problem, the kind that you might see in your exams, using these concepts of distance and displacement.
Here is the question. A farmer is walking along the boundary of a square field. Each side of the square is 10 meters long. It takes him 40 seconds to walk one complete round of the field. The question is, what will be the magnitude of his displacement after 2 minutes and 20 seconds? Let's solve this step by step. The first step in any problem is to make sure all units are the same. So let's convert the total time into seconds. 2 minutes is 120 seconds, plus another 20 seconds, so the total time is 140 seconds. Now we know one round takes 40 seconds. So in 140 seconds, how many rounds will the farmer complete? We divide 140 by 40. We get 3.5. So the farmer completes 3.5 rounds. Now think, after 3 complete rounds, he is back at the starting point. Then he walks another half round. Where will he be? He will be at the corner diagonally opposite to where he started. So his displacement is the shortest distance from his starting corner to the diagonally opposite corner. For a square, this is simply the length of the diagonal. And how do we find the diagonal of a square? We use Pythagoras' theorem. The displacement will be the square root of 10 squared plus 10 squared. That is the square root of 200. And when we simplify that, the final answer for the displacement is 10 root 2 meters. So before we finish, let's quickly revise the main points from today's lesson. First, motion and rest are relative. Second, we always need a reference point, or an origin, to describe position. Third, distance is the total path length. Fourth, displacement is the shortest path between the initial and final points. And finally, and most importantly, displacement can be 0 even if the distance is not 0. We've done a very good job today of learning how to describe motion. But this brings up a new question. If 2 cars are moving, just saying they are in motion isn't enough. We want to know, which one is faster? How do we compare how fast or slow things are moving? And that is exactly the question we will answer in our next session. We will talk about uniform and non-uniform motion, and we will learn about 2 new concepts, speed and velocity. Thank you for your attention today, and I'll see you in the next class. Keep looking around you and observing the world of motion.